Video covers Griffiths E&M section 5.1.1 magnetic fields. So far in this course, the goal has been to calculate the force that a charge Q feels from some other set of charges, usually denoted as little q. Okay, so we're trying to calculate the force that this test charge feels, and the strategy that we used was to say, all right, these charges generate an electric field, which I can calculate either directly or indirectly through the potential. And then I can figure out the force that my test charge feels by taking the product of that charge with the electric field that's calculated. So this test charge sits in a field E and feels a force F. We have done this only in the context of stationary test charge, where our test charge is stationary. All right, so it doesn't move. We also said that the things that are generating the field are also not moving, but importantly, this charge does not move. So if this other charge moves, if our test charge Q has some velocity that is non-zero, there is a chance that it will feel an additional force as not the electric force or the force from the electric field, but it is the magnetic force. The force that this charge, if it's moving, is going to feel is equal to the test charge times the cross product of its velocity and the magnetic field that it sits in. Okay, so I have some field, just drawing it arbitrary. I have my test charge that lives in that field and is moving around with some velocity. And if it's moving in a magnetic field, it will feel a magnetic force. Therefore, the way to find the total force that a charge feels is going to be to first find the electric force, which is what we've done in this class so far, and then find the magnetic force. I know what each of those expressions are. I know from earlier in the quarter that I have a test charge times the electric field, and then my magnetic force is the thing that I drew just up there. My trackpad is not working super well. Q times V cross B, or equivalently Q E plus V cross B. So if we can find our magnetic fields, and we already know we can find electric fields, then we can calculate the total force that a charge feels. Okay, that's going to be the goal for pretty much the remainder of the class, is to find magnetic fields. Okay. Griffiths makes a big deal about the fact that magnetic forces do not actually do work. Okay. So let's just give my version of that argument. If I'm going to calculate the work from the magnetic force, I will calculate the magnetic force and it's dotted with some displacement. Okay, so it's a force times dotted with the displacement is the amount of work that that force does. I can rewrite that as V cross B, Q V cross B. Right, that's that magnetic force that I just wrote. And then I have to dot that with the displacement, which is really just V times dt. Okay. But this cross product here is always perpendicular to the velocity, right? That's the definition of taking this cross product. And then if I take something that is perpendicular to the velocity vector and dot it with the velocity vector, I then get 0. Okay, so magnetic fields do no work on particles. Okay? And there are examples that Griffiths discusses a little bit more that might, if that sounds counterintuitive, hopefully he clarifies that.